Swayam Prabha. Digital India. Educated India.
Okay, welcome to this session. It's not really a lecture, so this is the second exercise session. But I'll begin this with an add-on to the lecture number 7, where we talked about the boundary conditions, and there I made a mistake that I'm going to correct. Otherwise, you would be troubled with the example that we would be talking about today. So yesterday we talked about the bounce back boundary condition, and in particular the velocity bounce back boundary condition, which we will also use today for the lid-driven cavity example, because we have a moving boundary here and we have resting boundaries in other places. So, and in our nomenclature, I'm not using too much space, where this here would be space and this here would be time. We would recognize this Fi, yeah, so important, this is time, not space. Fi going out and F minus I going in. Then the bounce back boundary condition. So for the last node at the position xn, so the bounce back boundary condition for the population that is coming in then would be at the position xn and time t plus delta t is simply the one that went out. So this is I after the collision. So this is before the collision at the position xn and at the previous time. Okay. So a little bit I'm coming into my own domain here. So this is the usual, that would be the usual bounce back, right? So now we also discussed the velocity bounce back, and the velocity bounce back is the same boundary condition, just this boundary condition only gives us velocity 0. And now we want to modify this to a non-zero velocity. And this can be done in the following way. Actually, a little bit similar to the anti-bounce back, if you remember this. So we have again, starting from the incoming population at the next time step is what has been going out. And now we want to modify this. And the way we modify this is, so we want to set a different velocity. So this different velocity can be set by by adjusting the equilibrium function of this. So we are subtracting the equilibrium function in the direction I, given the velocity on the boundary, right? So this would in general be a vector, yeah? So we subtract this in order to remove the equilibrium, to remove the part that is still, to remove the velocity that is in this population here. And then we want to have the velocity in the opposite direction. Therefore, we add the velocity in the opposite direction, the equilibrium in the opposite direction, and this for the same velocity. Okay, so we remove we remove equilibrium going this way and we add equilibrium going the other way because this is the way that we want to have it. Now, a simplification of this, and now I need a little bit more space, or let me see, okay, I'm on this. So we need to know what the equilibrium of an Fi is, and there are different ways to, we thought there are different ways for writing them down, but the one for simplicity that we are using now is the Taylor expanded. All the others would work the same way. There we have the weight Wi times the density, and then we have here 1 plus EI, scalar product with the velocity, divided by CS square plus EI times U squared, this squared, divided by 2CS by the power of 4 minus U times U divided by 2CS square. So never mind that these are all dimensionless velocities, therefore never mind that this is not dimensional consistent. So I've now spent all of my space here already. The thing that you would have to recognize if you add these two together is that you would have to evaluate this once for Fi and one for Fi inverse, right? So Fi inverse gives EI inverse is the opposite to Fi. So this, whenever this is positive, this Fi inverse would be negative, yeah, and the other way around. And here, because these things are squared, they will be the same in both. The same goes for, of course, for the one. They are the same in the Fi equilibrium and in the Fi inverse equilibrium. Yeah. So this and this will disappear, and here we get a minus from this one, and then a plus from this one, but a minus from that one, so that they come out together. That they come out together and become Fi inverse at this position, which I'm not writing now to save some space, Fi after collision. And what is now left is minus Wi rho EI into U divided by CS square. And because this comes twice, this is twice this. Now, one thing that I skipped over yesterday is that we call the dimensionless version of this CS square, we call this CS square. In dimensionless form, we call this theta, which is speed of sound square is related to the temperature. So this is a dimensionless temperature, such that we can write the above also as Fi asterisk minus omega I rho, now theta by -1. And this is the mistake that I had in my writing. So yesterday I wrote theta, so obviously it is the inverse of theta, EI times U divided by CS square. And by the way, sorry, there's a 2 missing now, yeah? And this is also because we know that this is 1/3 in the Lattice-Boltzmann method. This can also then be written as -6 Wi rho E I U divided by CS square. Yes. Oh, I've overdone it, right? Yeah. Right. So that's okay. The few little mistakes. So this is what you are going to use for. I'm going to erase this here. So this here is what you are going to use now in this example. In this example for the lid of this cavity. Okay. Yeah, please make this correction. Sorry for the trouble. And now Kamesh is going on with explaining the code.
Programming tutorial today. Fine. Let's try to look at the entire code, the entire C++, Python interface, and if possible, try running the entire lid-driven cavity code also. So what I try to do is that we'll start from the beginning of the C++ code, rather than going for different parts as we have done before. Out of this, we have already seen how the equilibrium distribution function was calculated, right, with Mathematica and within the C++ code. Okay. So feel free to again stop me wherever you have a question. So the code is written such that you have most of the code written in C++, the entire code is written in C++, whereas you have a Python interface which is going to selectively call some of the functions, and because you can have better control for while the code is running, and also for easy post-processing and viewing of results while the code is running. Okay, because if you write everything in Python, it may be slow. That's why you have the entire code written in C++, and Python is driving the code as such. Okay, so this is very typical if you take any software, commercial software or open source software. Usually you'll have some kind of an interpreter language which will be driving the compiled language code that is written in the background. Okay, so this is very typical that you find in any commercial or open source software. Okay, all right. Is the font size okay, or should I increase that? Font size is okay, fine. So we have a few includes here. The first one is pybind11, pybind11.h, and then numpy.h. These are used for generating the Python bindings for the C++ functions. Okay, so don't worry about that too much right now. We will see wherever that has come, you can also make use of those functions. Okay, and then we are including hash include vector. This is basically including the vector standard template library, because we want to declare arrays or vectors from there in the standard format. Okay, fine. So we are defining a class. We're calling this class as lowercase lbm with a capital D demo. Okay, so we have lbm demo, that is the name of the class, and now it contains several private variables, some public functions, some private functions, and so on, and then a constructor and a destructor, just like a typical C++ code. Okay, so we're going to look at the lid-driven cavity code, which is drawn at the on the board here. You can see on the right hand side you have 3 walls, out of which 4 walls, out of which 3 are stationary, and the top wall is moving in the positive x direction with certain imposed velocity, with a constant velocity. Okay, which we call it as u lid or ubc. Okay, all other velocities on the walls are all 0. Okay, and then to help us, I have also drawn the distribution functions f00, f10, and so on here, so that you can help me writing the boundary conditions. Okay, and then the domain extents are also kind of indicated here. Fine. So coming to the private variables, what we are first defining is we are defining int rows. That's going to basically tell you how many number of rows you have in your domain. Okay. Similarly, int columns is going to tell you how many number of columns you have in your domain that you are discretizing for this. So a schematic is drawn here. This is the lid-driven cavity. Okay, you have the top boundary is UBC. Then you have these are the stationary walls, and you have these dots basically indicate the fluid inside the cavity. Okay, Then we are also declaring double using double precision UBC. This is the value of the velocity boundary condition we will specify on the top. And then omega, this is the same omega that you have seen yesterday when you had the collision operation done, right? You had omega times F equilibrium minus F that you add to the existing distribution function to get the post collision distribution functions. Okay, so that is the omega. Now we will also define primitive variables which are basically your ux, uy and rho. These are your velocities in both the x and y directions, and then the rho is the density. Okay, I've written it out mostly for post processing, but you need them for even for the calculation of the flow. Okay, so you have standard vector double ux. So this is basically going to give you ux as a two-dimensional vector or basically a matrix. Okay, and then uy is also be in a double precision, it's going to be a matrix, and rho is also same matrix. Okay, and we're going to define the number of columns as we go down to the initialization, okay, or to the in the call to the constructor. So we are using this D2Q9 lattice, which is same as what is drawn here and which you have been working with. You have the F00, the stationary link at the centroid, and then you have F plus 0, F minus 0, F0P, and then F0M. Okay, these are your F0 plus 1, F0 minus 1. Those are the four cardinal directions, and then you have F plus 1 plus 1, F plus 1 minus 1, then you have F minus 1 plus 1, and then F minus 1 minus 1. Okay, these are the other four diagonal components. Now, as you can see, we have the arrays. So we have a set of arrays which are for the distribution functions for each of, because we need to store each of these f's at each and every grid point that we have. Correct? If your grids are number of columns by number of rows, or number of rows by number of columns, at every grid point we have to store what is this entire lattice. Correct? So as you can see, we have now defining F00, F plus 0, 0 plus, minus 0, 0 minus, and again all the other diagonal directions which are F plus plus, F minus minus, and then F plus minus, and then minus plus, right? All these 8 directions for each of these, or for all the 9, we are storing them at each and every grid point. Okay, that is the memory allocation that is done here. Now you may find it maybe convenient if you want to club all of these into one and then say I would like to write it as f of dimension of 9 instead of having 9 different values. Those optimizations you can do, which we did not try to do it in this one, because in this one because we are calculating the plus 1, 0, 0 minus 1, all these from the moment matching, it is much more convenient to work with these values rather than writing them as index 0, index 1, index 2 and so on. Okay, so that kind of optimization you can do later if you wish. Now these are the populations for the pre-collision, and then we need to declare for these values post-collision. Okay, the post-collision values we are defining it as we are denoting with a S here, capital S, which indicates a star. This is the post-collision values of the distribution functions, and then just like the pre-collision, we have to store all these 9 distribution functions at each and every grid point we have. Correct? So I have F00S, then we have F plus 0S, this is the star, F0 plus star, F minus 0 star, F0 minus star, and we have plus plus star, then we have minus minus star, plus minus star, and then minus plus star. Okay, so all these are again the same 9 populations for post collision denoted with S or the stars. Okay, fine. Any questions so far? No? All right, fine. So then as I said, we are going to make use of Python bindings. We are going to run the code actually from Python. That's going to use the compiled C++ code as a shared object file, okay, as a static library, okay, and as a .so file. So for that we need these bindings. That means which functions you want to expose to the Python interface so that you can call them. So for that we need to also declare this kind of an array, which is basically going to convert the vector type that you have in the C++ to the NumPy variation that you have in the Python, so that any arrays that you send from C++ will be read by Python correctly. Okay, so for that we are defining it here. PyBind 11 array T double vector to NumPy. So this vector to NumPy is a function which we are defining. It's going to convert your number of rows and columns you have into something that Python can interpret. Okay, so don't worry about this too much at the moment. We will see later. Okay, so it's basically going to return you this array which is in the C++ memory. Okay, we were looking at some functions which we call them as public functions, and this is your constructor as such. Okay, because it has the same name as the class LBM demo, and it has a range of arguments. Okay, the arguments we are passing are int C, this is the number of columns, and then int R, this is the number of rows, W, this is the U velocity that you want to access. Okay, and U is the U boundary condition that we are going to set. Okay, and then double omega is the omega value that we want to set. Okay, so these values are passed, and then you are essentially setting number of the value of rows you have defined here, the private variable rows here. Correct. If you go up, you see rows here. Okay, this rows is being set to the R value that is passed, and that function call is made. That is rows is being set to R. Similarly, columns, this is what you have in the C++ code. It is set to C, whatever you pass as an argument here when LBM demo is called. Okay, then UBC is going to set the velocity boundary condition on the top of the lid to be U. Okay, and omega of OM, it's going to set value of OM to omega. Okay, then it kind of still continues. What we have is, we have now UX is being initialized with number of columns, which that is that C, and then the number of rows. Okay, that is the memory that is allocated for UX. Okay, and it is being initialized to 0.0. So you are initializing your entire flow field to be 0 for UX component. Similarly, the UY component, you are again have a number of columns by number of rows, and then you are initializing with 0. Okay, then the density, which is row, also is of the same size as the domain, that is number of columns by number of rows, and you are initializing it to be 1. So you are starting your simulation from row equals 1, UX equals 0, UI equals 0 over the entire domain. Fine. Now, as you have learned yesterday in the lecture, you have to also you need values for initialization as well as the boundary conditions for the distribution functions. Correct. So how do we initialize these distribution functions or the populations? That means you have to get started with what is the initial value of f00, f plus 0, f0 plus for all the 9 directions. Correct. So anybody remembers how it can be done? So you can substitute for whatever is the macroscopic field you are initializing with, that is UX equals 0, UI equals 0, row equals 1 into the equilibrium distribution function. That's going to give you your initial values for the f. Correct. That's what you have learned yesterday. So that means I will go back to the Mathematica code we have, which we have looked at a couple of days back. So you remember we have these moment definitions, correct, as the summation of ij, I to the power a, j to the power b, fij, correct, and then we have these m00, m02, all these. Okay, and okay, these are all done. Okay, and then we have this table of moments. Okay, we have this, solve this thing. Okay, So let me now substitute for, so we solved for distribution functions as a in terms of moments, right? This was f0, 0, f minus 1, minus 1 in terms of moments we have, which is from 0, 1, 2 for ABC. Now what we want to do is that we want to substitute for ux, uy to be these values. For example, I have these ffs, which is basically the entire table of distribution functions. In the previous lecture, we looked at substituting moment 0, 0 equals rho, moment 1, 0 as rho times ux, moment 0, 1 as rho times uy, moment 2, 0 as rho times 1/3 plus ux square, and so on, right? Now, instead of this rho, I want to substitute for 1. And then instead of this ux, I want to substitute for 0, correct? That's going to basically give me moment of 0, 0 will go to 1, correct? That is the value it will go to. And then moment 1, 0 will go to a value of 0, okay? Moment 0, 1 will go to 0. And what about moment 2, 0? How much would that be? 1 hour? 1 hour 3? 1 hour 3 or 9? 2, 2 will be 9. 2, 0 would be 1 over 3. 0, 2 will also be 1 over 3. Moment 1, 1 would be 0. Moment 1, 2 also 0 because you have multiplication with ux. Moment 2, 1, 0. Moment 2, 2 would be 1 over 9, correct? So that's what we have. So we go back and then substitute for these, okay? So I have written 0, 0 goes to 1, 1, 0, 0, 1 goes to 0, 2, 0 goes to 1/3, 0, 2 goes to 1/3, 1, 1, 1, 2, 2, 1 all go to 0, moment 2, 2 goes to 1/9, okay? So I have this, but then I want to substitute this and then run the, substitute them here for all these moments and then calculate what is the distribution function. That's what I have done. That basically gave me f00 equal to 4 by 9, correct? Similarly, f10, where is 10? 10 is 1/9, okay? Similarly, 01 is 1/9, and then 0 minus 1 and minus 10, these are all 1/9, okay? These are all the 4 primary directions you have. Then the diagonal directions, which are minus 1, minus 1, minus 1, 1, 1 minus 1, and then 1, 1. These are all 1 over 36, correct? So we got these values. Now, this is exactly what is used in the code. So we substitute for f00 as 4 by 9 as the initialization value. Similarly, for plus 0, we have 1/9. Same is the case for all the 4 cardinal directions for 0 plus, 0 minus, plus 0 and minus 0, okay? Then for all the diagonal directions, we have 1 over 36, correct? So we have this part. That is the initialization for the distribution functions for the pre-collision f's. Similarly, we are also initializing the post-collision populations also with the same values we have here, okay, that we have done for the pre-collision values, okay? So I'm using the same values here. Then the constructor itself is not doing anything. It's just a open brace and then close brace. Similarly, we have a destructor function that is tilde lbm demo, and it is also not doing anything as such, okay? Because what we have is kind of a static allocation of the variables. There is no other thing that is being done. Then we have these functions. This is basically get num rows, which is a function. It's going to, it basically return rows. It's going to return how many number of rows you are dealing with, and so that's why the return type is integer. Similarly, get number of columns is going to simply return the columns value that you have set, okay? Then, as I said, we want to call some of these functions from the Python interface. We are again defining a pi_11 array t double, okay, which is basically get row matrix, okay, and it's going to basically return this vector to numpy row. So you remember we have already defined what was row, ux, ui as vectors within the C++. These will be return to the Python side if you want to take a look at what is the values that are there in this row ux uy from time to time. Whenever you seek this value, it's going to give you what was written to ux row uy by the C++ code that is running. Okay, fine. So these are the Python bindings that we have. We have a loop where it goes from left to right and then bottom to top. Yeah, so we'll go from 0 0 to number of columns, I think so, or something like that. I have basically two arrays. Okay, one for the rows and one for the columns. No, it will not degrade, but there will be some penalty because you are calling, you are running it from the Python side. Definitely there is a function call that is involved. So there will be a stack and the function call, but then it's not going to degrade the time the C++ takes to run. Yes, so these are all, it will run at the same speed as it would run if it is just a pure C++. Only thing we are trying to do is that you can call or interrupt this at any time you want, and you can also monitor the solution as it is running. So you don't have to wait for it to write an output file, then load into some post processor and then take a look at it. Equilibrium distribution function we are not initializing. Equilibriums we will calculate as and when our row and u fields change with time. We're going to recalculate what is equilibrium. Okay, that there is no initialization required for that. We are not. We will. I mean, at t equal to 0, you will go and then calculate it, and in the solver. Then what we have is we have the main function which we call it as, it is void, so it's not returning anything. The function is called run, run. This is it's going to run a SRT BGK model. Okay, and we are passing in steps, int number of steps. We would like to, let's say, run some 100 steps or 1000 steps or something like that. Then I fill in the boundary conditions for the velocity for the top row here, which is going from x equals 1 to x equals number of columns minus 1. I'm filling in what is ux for all the rows minus 1. That means the top lid velocity is what I'm populating. Okay, there is a subtle difference in the boundary condition here. You will notice that you will probably ask me a question about that. Okay, there is a small difference in terms of how it is interpreted. Okay, then we have within the number of steps, we have this int t equals 0, t less than steps, t plus plus. So this is the main time loop which is doing so many steps that we have asked it to run. Okay, so that is the main time loop. And then these two, as you can see, these two for loops are for the sweeping across the space. Correct? So I have y equals 1, y less than number of rows minus 1, y plus plus. That is as I go to different rows. Okay, and then x equals 1, x less than number of columns minus 1, x plus plus. This is for the different columns, right? So as you can see, x is the innermost loop. So we'll do all the columns, then I go to the next row, do all the columns, then I go to the next row and so on. Right? That is how it is doing. Fine. So as I have three main loops. One is the time loop, then I have two spatial loops because we are looking at a 2D problem. Fine. Then what is the first thing we have to do? First thing we have to do is that with the available distribution functions, we need to calculate what are the macroscopic quantities, because these row u, x and ui are required in the collision, which will basically require collision depends on the equilibrium distribution functions, and equilibrium is further calculated from row ux, ui, correct? So as a result, we are first calculating what is row from the initial populations we have. So row, as you know, is equal to sum of all the 9 links, correct? Because you have 0, 0 moment, m 0, 0. So I to the power 0, j to the power 0, it's basically positive all the time, correct? So you get sum of 0, 0, plus 0, minus 0, 0 plus, 0 minus, plus plus, minus minus, then you have minus plus and plus minus, right? All the 9 values are here. Then what will be ux? Ux would be m10. So again, you will have, if the first index is minus, you're going to get a minus, otherwise it's going to be plus, okay? So you have f plus 0 minus f minus 0, then you have f plus plus minus f minus minus, then you have f minus plus and you have plus minus, then Okay, of course the other values also will become 0 depending on, because it's m1 0, right? Only some of them will survive. Then that is going to give you rho times ux, correct? So if I divide with rho, which I just computed in the previous step, I'm going to get the ux, the velocity in the x direction. Okay. Similarly, uy would be the y component of velocity, which again you will get from the distribution functions, which is basically m01, right? M01 would be, you will get a positive value if, or you will get a negative value if the second index is negative, correct? It means f0 plus minus f0 minus. Similarly, f plus plus, f minus minus, then you're going to get f minus plus and then minus f plus minus, okay, divided by rho. So that gave you the uy velocity, correct? So we are at the first time step, and at the first time step you have calculated, you initialize with distribution functions, and from distribution functions you are calculating your rho, ux, uy, correct? These are calculated. What is the next step? Next step is to calculate the F equilibriums from these macroscopic values you have calculated, okay, which is basically the PGK collision operator with moment matching. And this part we have seen yesterday or on the previous lecture, where you wrote F equilibrium 0, 0 in terms of rho, ux, uy, right? And then F equilibrium minus 0 again in terms of that, and so on. So these are the same set of expressions, okay, that we have seen previously. All right. Okay, so I'm skipping over this thing. Now this is your F equilibrium that is calculated from the macroscopic variables, which are rho, ux, uy. Now, how is the collision operator expressed? Do you remember from the lecture? How is the collision operator? Okay, so basically collision operator I think is something like this, which you have already written down in the lecture. Fij star equals Fij plus omega times Fij equilibrium minus Fij, correct? That means Fij equilibrium I have just calculated from the rho, ux, uy. Fij is the initial populations I have initialized, right, at time step 1, right? Then all we have to do is that subtract off Fij from F equilibrium, multiply that with the omega, and then add it to Fij. That's going to give you, that is the collision operator, which is going to give you the F star values, correct? Is it the same as what you have written in your notes? It is, okay. So, and we have to do this for all 9 populations, correct? That is I going from -1 to 1, j going from -1 to 1, okay. All right, so where is my code? Okay. So then, as you can see, because I'm working with all the populations with separate names, I can only do it one by one, right? But if you have something else, it could be different. So what I have is for the 0 population, I have F00 star on the left hand side equals F00 plus omega times F equilibrium 00 minus F00, right? Is the first line clear to everybody? Okay, it is basically the same expression we have to apply for each and every population. Now what you see is that we have kind of combined the streaming with the collision here, okay, in one step, which we call it as collision plus a push scheme, okay. So what we will see is that as of now we will not worry about this x minus 1, x plus 1, all these things at the moment. But without that, if you see, I have F minus 0 star equals F minus 0 plus omega times F minus 0 equilibrium, F equilibrium minus 0 minus F minus 0, correct? The same expression for different ij values. Do you see that? Which we call it as a push scheme because we are doing the streaming on the post collision populations. Okay, that part is hidden in this x minus 1, x plus 1, y minus 1, y plus 1, and so on. How that is happening we'll just see in a moment, but as of now I want you to appreciate that without looking at this x minus 1, see for example on the right hand side I have f minus 0 evaluated xy, correct? Similarly f minus 0 evaluated xy, that should have been pushed to, that should have been just evaluated to f minus 0 star at xy. But instead I'm doing f minus 0 star x minus 1y. Okay, that is the streaming step that we have, which I'll come to in a little while. But without regard to that, if you verify everything else is the same collision operator that we have seen in this one. Okay, now coming to the streaming step, what we have is, so the streaming step I kind of, you must have already seen in the lecture, but then I kind of show it here again. This is not exactly in the same index notation as we have used before, right? Earlier we had this 1 0 0 1 0 minus 1, all those things. Here I have not drawn it again properly, so which is basically shows in terms of f1, f2, f3, f4, but don't worry about the numbers there. We realize that f1 is basically our f10, right? And f3 is our f0, f minus 10, and f2 is our f01, and f4 is our f0 minus 1, and so on. Fine. Now, what do you do in streaming? You do basically these links will go to the corresponding lattice in their lattice directions. Correct? That means f1 is going to go in this direction. Similarly, f0 minus 1 is going to go in this direction, and f01 is going to go to the top point, and then f0 minus 1 is going to go in the downward direction, and then f11 will go into this diagonal thing, and f minus 1 will go into the bottom down diagonal, and f minus 1 will go into the top corner here, and then f minus 1 will go into the bottom left corner here. Okay, so it is actually very easy to see where it is going from the Miller index notation we have than from the 1 to 8 links that I have used here. Okay, because here you can easily see if something is 1 0, it is going in the positive x direction. If something is 0 minus 1, it is minus 1 0, it's going in the negative x direction to the next grid point. Okay, that is very easy to see, which is not so easy because you have now introduced a single index notation here, which is masking all the directions with some other notation. Okay, which is not very convenient to work with. Okay, now you know what is essentially the streaming step. So where will this post collision population should go? For example, f minus 0 star is this right hand side, right? This right hand side is f minus 0 star, correct, at xy, and it should go to x minus 1y, correct? That would be the streaming. Yes, so that's why that value I am putting it in x minus 1y here. Do you agree? Similarly, let's say this value, it turns out to be f plus 0 or plus 10 at xy location, correct? And f plus 10, where will that end up? That will end up at x plus 1 at the same y, correct? So we are moving that to, we are updating f plus 0 star x plus 1 y, right? It is going to the streaming step is implemented in there. Yes or no? Okay. Similarly, the next line here is f0 minus. 0 minus is the post collision, f0 minus star, and f0 minus star is going to go to x y minus 1, right? Because it is 0 minus 1, correct? Similarly, f0 plus is pointing upwards, so that will go to f0 plus star would go to f0 plus star at location x comma y plus 1. You go to the next grid point. Okay, and f minus minus, this right hand side is now f minus minus star, which is the post collision population. That is going to, it is because it is minus minus, it is going to x minus 1 y minus 1, correct? Okay. Similarly, f plus plus star, which is this right hand side quantity, that becomes that will go to x plus 1 y plus 1, correct? Because this is the f plus plus quantity. Similarly, we have f plus 1 minus 1. star, which is the post collision for f plus 1 minus 1, that will go to x plus 1, y minus 1, right? And you have f minus 1 plus 1, that is minus 1 plus 1 is on the left top corner. That is basically f minus 1 plus 1 star will go to x minus 1, y plus 1, correct? Now, of course, you can do this in 2 steps, but this is going to save you some coding, right? Because you don't have to do it again as another loop or another set of statements below. Is this clear? So, which we are calling it as BGK, because F equilibrium was calculated using BGK SRT, and that is the BGK collision plus the push scheme. Push scheme already had the streaming step that you would have, correct? So far what we have seen is, we have seen the class definition, the number of rows, number of columns, the boundary condition and so on. Then you had a constructor, then you had a destructor, and you had a set of functions which will be convenient if you want to call from the Python interface. Then we had the initialization for the distribution functions, for the star or the post collision distribution functions. Then we said we have to calculate we have the main time loop over across space, correct, in the x and y directions. Then within that we were having calculation of equilibrium distribution functions, right, using these quantities. Then we implemented the collision plus streaming, collision plus push scheme. Only the interior parts, yes, only the interior part, because my boundary conditions are applied on the 4 outermost white lines, right? So we are only doing from 1 to row minus 1, which is let us say within the here, and then 1 to columns minus 1. Okay, so the question is, right now what I have collision plus streaming, then we have the boundary conditions, correct, which are applied. Do you get the same solution if you do collision and apply boundary conditions, and then streaming and apply boundary conditions? The boundary conditions are, I think it depends on how you look at them. The boundary conditions, as we have seen yesterday, they are applied on you have these delayed, non-delayed boundary conditions, correct? Those are applied, like as we have seen yesterday, after one collision step and the streaming step as such, correct? I'm not sure, maybe you can add if you find it different. No, if you want to apply twice, then you have to also define boundary conditions for these populations which are after collision but before streaming, correct? Which I don't know whether you can apply in that sense. Maybe Professor Gayer can add condition I have. Okay.
We may go just to the boundary condition later to see what the boundary conditions is, because now we are discussing in theory.
Sure. Yeah. Okay, I think we will take up that question later. Okay, so as of now we finished collision and streaming, correct? That is done, and then these two curly braces here are closing the 2 space loops, that is loop over x and loop over y, correct? That is what is being closed here. Then we have of course the time loop running. Okay, so we are using the dry node boundary condition here that you have learned yesterday. Okay, and again, either you can work with the delayed bounce back condition or the non-delayed bounce back condition. As of now I am dealing with the delayed bounce back condition. You can easily change it to the non-delayed version later. So as you can see, we need to apply boundary conditions on 4 walls, okay, that is left, right, top and bottom. We also need to apply boundary conditions on the 4 corners because we have some population links there, okay. So all these boundary conditions need to be applied. So I have a schematic here which is hopefully will load here. Okay, so these schematics are not quite correct. Okay, let me look at the bottom boundary condition. Okay, so as you can see here, the black wall is basically the bottom wall. And because we are looking at a dry node kind of boundary condition, this happens to be halfway between the 2 links we have, correct? So So what we have is that 0 is the bottommost value if I'm applying a boundary condition at the bottom, and 1 is the one level above that, correct? Now I have pictorially shown here black links which are essentially going out of the boundary, correct? And the time is not indicated here, because yesterday you looked at the xt diagram, whereas there is no time in this. The time is in terms of the arrow or the link flipping it coming back, okay? So what you see is that the black links, which are this one and this one, are the ones populations that are going out of the domain, right? And then because you are applying a bounce back condition, they will return back to in these directions, in the directions of the red arrows here, okay? Now by looking at this picture, could you tell me what will be these black links, what will be the indices for the black links at location 1, which I need to, or going to location 0, correct? Which indices of these black links we have to apply boundary condition for? Which links will these be? What will be this black link going down? That is F0, 0 minus 1. F0 minus 1 is going out. Okay, what will be the other two links? F1 minus 1 and then minus 1 minus 1, minus 1 minus 1. Okay, so these are the links. That means if I look at the bottom boundary, so we have 0 minus and then plus 1 minus 1 and then minus 1 minus 1, correct? And I have to apply it for each and every column on the bottom boundary. That means I am applying it for all x values, and then 0 is where these links are coming to, correct? When they are all coming towards 0. Now that is what is my black lines here, right? These are the populations which are evaluated at 0, which are all going out of the boundary, correct? Now these have to be bounced back to appropriate locations, okay? And what will be the red links then? 0, 1, okay, 0 plus 1, 0 plus 1, 1, 1, and then minus 1, 1, correct? Those will be the red links, and these will be going to location 1, okay? Fine, that means, sorry? Red ones are the ones the same as the black ones, because I have a 0 velocity boundary. At 0, we are not performing a collision. No, we are applying a bounce back condition. Your bounce back condition, there is no collision there as such, correct? The populations that are going out of the boundary are bouncing back into the domain, correct? That's what we have seen in the lecture. Black line is actually the physical boundary, right? Because this is a dry node boundary condition, correct? So my links are stored at 0, 1, 2 and so on. Like for example, if you see here, I have drawn two sets of white lines, right? In between I have drawn the blue line, and the blue lines are the ones where actually physically my boundary is sitting. It actually doesn't correspond to any of them, because that is how the dry node formulation came about, right? If you look at the wet node formulation, then it will lie with one of them, it will lie with the outermost one, correct?
So you are equating red one equal to black one?
I'm equating, yes. This is the same population that are going out. If you remember from yesterday's boundary condition diagram, you had x and t, and then whatever that is going is coming back in a delayed sense, correct? Oh, for the post-processing, I have done some kind of a small change here, but in terms of interpretation, we have to interpret it in a different way. Okay, I'll show you what I'm doing, but it may not be exactly correct. But in terms of interpretation, it is exactly not correct. We have to interpret it in certain way to make sense out of how it is post-processed. It doesn't matter how many number of grid points you have. The only thing that matters here is that you are defining your grid based on certain dimensions, number of columns versus number of rows. Now, all that happens is that your boundary only happens to be halfway or midway between the first
Yes.
and the one inside, something like that. So you can always back calculate how many number of grid points you want from this thing. I think you'll probably your question will be clear a little later once we look at the code. Okay, yeah. Other questions? Is it okay? Fine, people are able to follow. All right. So that's for the bottom boundary. So as you can see, I have 0m plus 1 minus 1 minus 1 minus 1 at 0 0 0. That is whatever the links that are going out. We are updating it to be 1 1 1. And then as you can see, because I have drawn like this, correct? So f0 minus 1 is coming back as f1 0 at location 1, isn't it? That's going to come back at location 1, x comma 1. Whereas f minus 1 plus 1 or plus 1 minus 1, it will go to minus 1 plus 1 star. Okay, so this is the delayed bounce back. We are updating the post collision values with the pre collision values, correct? That is your delayed bounce back. And you see I have x minus 1 here. That's because that means this black link which was coming towards 0 now goes back to 1x location to the left of it. X minus 1 and 1. Similarly, this would basically be x plus 1 and 1. Correct? Do you see that? So I have from x0, all the links that are coming towards x0, I have 0 minus 1, and we have minus 1 minus 1, and then 1 minus 1. These three, when they go back, this one will go back to 0 minus 1 will go back to 0 plus 1 at the same x location and y equals 1, whereas the link that is coming this way will go back this way, which is going back to 1, which is for the y. For the x, it will go to x minus 1. So it, at neither. Zero velocity is achieved at black line in between. Correct? That is how the dry node approach is. If it was wet node, it would be on the boundary. Correct? So your zero velocity is actually in between.
So while post-processing, you have to take a black line as the one.
Yes. So while post-processing, we have to, yes. Otherwise, if I am populating my zero values as the boundary values, then I should keep in mind that the distance between 0 and 1 is actually not delta x, but it is delta x by 2. It is uniform for everybody else, but for the penultimate to ultimate thing is only half of what it is. Correct? Because instead of going from, it is not uniform at the boundaries. That's what I have to keep in mind. If I'm going to use the same zero values to populate the ux, uy, and rho.
Okay, he's referring to the condition that actually there is a slight, I mean, if you make the analysis more precise, you notice that there is an error term that is dependent on the relaxation rate that shifts your boundary slightly. And this is in particular the case if you deal with very high viscosity. So if you have very high viscosities, you can see the boundary actually shifted significantly. So usually when we talk about, because this is the cause, okay, this is, for example, often observed when you study creeping flow in porous media, where you have relatively high, where you actually are dealing with more like Stokes flow things. So because this course was particular on high fidelity lattice Boltzmann methods, the assumption that we are based on is that the viscosity is low, and when the viscosity is low, this kind of error has practically no effect, because then this modification of the position is very, very small. So this is nothing that in this context we would be concerned with. But if we go to the other end of the viscosity scale, to the very low Reynolds numbers, then we would be concerned that the position of the boundary is related to tau. Okay? If you want to know the pressure on the surface of the sphere, and the sphere is, then of course you have to interpolate, because then if you talk about the sphere is not on the nodes.
Correct.
Then
yeah, but if he has, instead of a sphere, if you have a cube or something, if he has a cube, if you have a cube and if you are again using, let's say, dry node approach, where the boundary is in between the lattice points.
Yeah, you balance the incoming and the outgoing. You basically, the thing why we use this kind of boundary conditions is that we have the populations actually stored in between. So
Yes.
from the population's point of view, this is where they are stored and where this is more natural to put the boundaries in between the nodes, because on the nodes we don't know the populations. We actually don't have populations on the nodes. We only have populations in between the nodes.
Yes. So we have to interpolate even in that sense. Yes.
But if you want to have anything specifically on the surface, then of course you have to interpolate.
Correct.
Yeah.
Yes. All right. So then let's look at the top boundary. So we looked at the bottom boundary. Okay. Let's look at the top boundary. For top, I have again a small schematic here. Okay. So again, we are looking at the delayed bounce back. That means the pre-collision populations are used to update the post-collision populations, correct? So we have F stars on the left side, Fs on the right hand side, okay? So as we have seen this morning, the top boundary is a velocity boundary, right? You have a non-zero velocity boundary. You have U prescribed as U BC, right? And what was the boundary condition we have seen? This was, in addition to the bounce back, you will also have this minus 2 omega I, so minus 2 Wi rho divided by theta times E bar dot UBC, correct? Remember this we was taught in the morning today. So that means together with this bounce backing the populations, we have to also subtract off this quantity, that is boundary condition inner producted with the EI bar, and then multiply by this factor, which is 2 rho Wi by theta, where Wi is the weight, which is basically the same value that we would got for that particular population when we have initialized. Okay, I think Wi are the weights, which are basically the same values that we have for the initialized populations. Okay, then if you look at the so let's say a typical top boundary is like this. You have rho minus 1 on the top, and then rho minus 2 at one location below that, one lattice location below that, and then of course you have x going from 0 to number of columns minus 1. Okay, then as I have drawn here in the schematic, the black links are the links which are going out of the domain, right? These are the populations that are leaving the domain. What are those that are leaving the domain? The black ones. Can you tell me what will be the values from here? What will be the names? F01, F11, and then F minus 11. Okay, these are the three ones. That means these three should be there on the right hand side. We extract this information, and then where will F01 go? So what will be the population that are, what should I update? 0 minus 1, minus 1 minus 1, and then 1 minus 1. I should do update on this thing, but then for 0 minus 1 it will be at the same x location, whereas for the minus 1 it will go to x minus 1. For minus 1 plus 1 it will go to x plus 1. Okay, I should make this shift when I do this, and in addition I should also evaluate what is E bar dot UBC. What would be E bar dot UBC for the vertical links? 0, because UBC is like this and E is like that. What will it be for the for this red link, which is going in the -1. Yeah, so what would that be for let's say this black link, which is going in the opposite direction? You'll get a minus, right? For the F11, you're going to get a plus, correct? Because it's going in the same direction. Okay, I'll look at the code here. I'll show you the code. So we have F0 plus 1, that is whatever is going out is coming back as 0m star, correct? Okay, and F plus 1 plus 1, which is plus 1 plus 1 is this guy, correct? That is a plus 1 plus 1, and that is coming back as -1 minus 1 star, correct? And then of course, as we have seen, it will go to x minus 1, and this -2 times rho wi divided by theta times E dot bc will evaluate to 6 by 36 times UBC. Okay, this 1 by 36 is the weight that you would get, which is the same as what we have done in the initialization. If I were to go there, you remember we had this 1 by 36, that is the same, we are calling it as weight, So, and then you have -6, that's because you have 2 times rho is 1, 1 by theta is 3, so you have 6 by 36, and then it will be minus when you have F plus plus, correct? Because there's a minus in the front. For the other quantity, it's going to be the E dot B UBC will evaluate to minus, which will basically make this a plus. Okay. Again, F minus 1 plus 1 will basically become F plus 1 minus 1 at x plus 1. Okay, at the next grid location. So, okay, questions on this part? UBC is what, sorry? My UBC is on that in between rows -1 and rows -2. I have to do, I have not yet done. So I'm only looked at the bottom and the top boundaries. We still have to do left and right and all the 4 corners. We still have to do. Yes. UBC? Oh, yeah, okay. Oh, you mean to the value? I have not set the value because we have not. Okay. So UBC is declared here, correct? And then in the function call, we have this W which we are passing, that is being initialized to UBC. UBC is being initialized to U. Whenever you call LBM demo with some values, that U will become UBC, and that UBC will be applied in the boundary condition. Fine. Okay. Any other questions? Okay, so that's about the bottom and the top. Now let's look at the left and the right. So I don't have these diagrams nicely drawn, but you can tell me what would be the populations on the, let's say on the left boundary, what populations would be going out of the domain. -1, 1, okay, -1, 0, and -1, -1. So these populations are going out of the domain, and they are going out at 0, right? We have to bring them back to x equals 1, right? And what would be coming in would be F10, 11, and 1 minus 1, right? These would be coming back at the left thing. And of course, again, F11, we have to move in the positive y direction. Similarly, F1 minus 1, we have to move it in the negative y direction by 1, okay? So with that, let us look at the left bounce back. We have F -1, 0, and then -1, -1, and then -1 plus 1. These 3 populations are going out, and these are coming back as F +1, 0 star, and then F +1 +1 star, and then F +1 -1. And then you can see we have also changed this 0 to 1. Okay, so it's going x equal to 0 values to x equal to 1, and then F +1 is going to y +1, and F +1 -1 is going to y -1. Yes. Now all the boundary conditions we have are for the delayed, correct? They are all for the delayed because I have the FM0, MM, and these things are from the pre-collision, which we are doing it as the star values now. Okay, but if you were to do, let's say this top one as a non-delayed boundary condition, then the implementation will be exactly the same as before, except that on the right hand side, instead of having FM0, you are going to use the current value of the post collision population. That means you're going to use FM0 star to update F plus 10 star instead of using just FM0. Correct? Do you see the difference? Okay, so that's going to be the non-delayed bounce back condition. Okay. Now, what would be the populations that would be leaving the domain at x equals column minus 1? F11, 10, and then 1 minus 1, right? These three, and they will come back as F minus 10, F minus 11, and then F minus 1 minus 1. Okay, so we'll look at the code. So whatever is going out on the right boundary is, that is at col minus 1, that is the rightmost boundary, column minus 1, F plus 10, plus 1 minus 1, and then plus 1 plus 1, right? These three are the ones that are going out, and when you have a bounce back, they'll come back to columns minus 2. Okay, they'll all come back to columns minus 2, and they're coming back as F minus 10, minus 1 plus 1, and then minus 1 minus 1, and then we put a star because you're updating the post collision populations, right? Because the remaining populations in the inside are already post collision, so you update them so that you're on the same page, correct, at that particular time step. Okay, then again F minus 1 plus 1 will go to Y plus 1, and then F minus 1 minus 1 will go to Y minus 1, correct? So we have now taken care of all the 4 boundary conditions, okay, left, right, bottom, and top. Okay, so Python actually will not store 0 0 as the left bottom corner. Yeah, it will store the left top as 0 0. So but then that notation is quite confusing, so we made a small fix in the post processing which will allow you to use 0 0 as the left bottom corner. Otherwise, when we say top, we would have to refer to y equal to 0 instead of y equal to rho minus 1. That will be kind of somewhat confusing. In fact, in C++ also it is stores the same way. You will have 0 0 at the top left, but then if you are not using Python, if you are using your own C++ code for post processing, then you can always say, okay, although you store as 0 0 as the top left, I will refer to you at 0 0 at the bottom left, and then you can rewrite everything around that. You can flip it and then use it. Okay, but unfortunately we are not doing that at the moment, so we have to do that small trick. Okay, that is basically a word of caution what it is here. Okay, let's look at the corners. So we have just like the 4 boundaries, we have 4 corners. Okay, what are the 4 corners? So first corner is 0 0, that is the bottom left. Which link is going out at the bottom 0 0? Minus 1 minus 1, right? The diagonal link is going out. That should come back as plus 1 plus 1. So what we have is minus 1 minus 1 at 0 0 comes back as plus 1 plus 1 at 1 1. Correct? So whatever is the link that is going out here will come back at 1 1. Okay, and let's look at the bottom 2 things. Then the other corner we have is columns minus 1 0, which is the bottom right corner. Which link is going out there? 1 minus 1. 1 minus 1 is going out, and that means we have F plus 1 minus 1 of columns minus 1 0. It should be coming at back as plus 1 minus 1, right? Sorry, minus 1 plus 1 to come back as minus 1 plus 1, and it will come back at columns minus 2 comma 1. Correct? Because you are at there, it will come back to columns minus 2 comma 1. Okay, exactly the way I have drawn. You have 2 more links which are on the top corners, right? If you look at the left one, which is 1 comma rows 0 comma rows minus 1, for that left top corner, which link is going out? What is the outgoing population? plus 1, minus 1 plus 1, minus 1 plus 1, and then just like you have seen before, you have this extra weight, this because this is a velocity boundary condition on the coordinates as well. So you have this minus 6 by 36 times UBC, which will be there when you update the corner points. And then it will come back, the incoming population would be F plus 1 minus 1 star, okay? And it is going to be evaluated 1 comma rows minus 2. Similarly, if you take the right top corner, okay, what would that be? What will be the population that is going out? There, columns minus 1, row minus 1. 1, 1, plus 1, plus 1, and it will come back as minus 1, minus 1, and at location, columns minus 2, row minus 2, okay. So that is F plus plus at columns minus 1, row minus 1 with a plus here. It will come back as F minus 1, minus 1, okay. That finishes the entire code, okay, for the corners as well as for the boundaries. To go between different time steps, I have to now exchange what are the pre-collisions with the post-collision. So rename them. So we're going to swap 00s as 00 and so on, okay. So the question is, the corner on the top belongs to, in fact, the corners belong to two boundaries, correct? So should I do it as for the top boundary or for the right boundary, correct? In this, we have assumed that they belong to the top boundary, right? But I think that's I think debatable. You can even do for the right boundary, because if you have actually a lid that is moving, then that point is usually a point of singularity, right? Say it again. If we are doing it separately, okay.
This 00, let us suppose we are handling it separately. So can we handle it while applying with the left boundary or the bottom boundary?
Oh, no, you mean to say you combine it with
Yeah,
doing
yeah.
left. You can do that if you want. Yeah, you can do that. But the problem is, for the corners, you have only one population that is going out.
Yeah.
Whereas for the left or the bottom, you have three populations
Three.
that are going out. So you have to have a separate condition for that. You can do that way also, yeah. Okay, so that is the kind of,
Excuse me.
yeah, please.
So if I have two velocities like in bottom wall, if for example, if there is a pressure driven flow in a channel, if I am imposing some velocity at the inlet and at the top wall it is no slip, and then the corner will be like, how it will be? Is it similar or?
I see. No, the corner points are always troublesome, especially if you deal with a finite difference kind of formulation where you are looking at that particular node, right? Because it belongs to two boundaries. But then in the case of Poiseuille flow or Couette flow, you have that corner would be anyway a zero velocity, correct? You'll have a no slip. So in that case, I don't see a problem as such, because you have a velocity profile that will be zero on the top, so it should be okay in that case. No, you cannot, because you have to give the population, because you still have to calculate what is the equilibrium macroscopic properties. You cannot avoid the populations, because the links have to be filled with appropriate values, correct? No, even in finite difference, you will still go to the last point, isn't it? So how do we say it doesn't get into the formulation? It will still get into the formulation. Let's say if you write a stream function vorticity formulation, you still have to deal with the corner point, isn't it? I mean, you will still apply the boundary condition.
Because post and so the accuracy of the f would be 1, but because the velocity is the same for the f and the f star, then it is also then the velocity will be second order accurate even if f is first order accurate. I mean, lid-driven cavity will usually not be second order accurate, because as you have discussed here now pretty well, it is actually not physically consistent to have two boundary conditions at the same location. So this problem does not actually have a physical solution. So if you, this is this is why you should actually, this is a simple example that people like to study, but in reality, if you have to know that this problem has no physical solution anyway, so it is not therefore a good test for a method in principle. So, and many people who are deeper in this disagree with this common practice to, do the lid-driven cavity. Yeah, it's okay for students to just see something running, but it's not. You're not convincing something that you get any correct result, because there is no correct result for this problem. You are not interested in the distribution, you're interested in the velocity. So therefore you don't care whether your distribution is first or second order. Yeah.
So the swap function that has been used here,
Yeah. Swap function, yeah.
I think the complexity is very high for this. I think we can use the vector swap that is there.
Oh, I see. Okay.
So the STL vector swap that we get, this
Sure.
will have linear complexity. The
Okay,
vector
okay.
swap will have a constant complexity.
Okay, sure. Yeah. So certainly optimizations can be done later on. I think we have not really
Yeah, no, like this doesn't. This is a general standard swap. The vector swap that you get, like you can write F00 as like 00s dot swap that is given by the vector STL library itself. That is constant. That is pointer. That exchanges the pointer for you. This is a general, like I'm looking at the source code actually.
Yeah, if there is a faster swapping function, certainly that can be used. Yeah. Okay, so okay, and in addition we have at the end of this program we also give we need to register these PyBind functions that will go into the module, okay, which is again written here. I think we should not worry too much about this. So LBM demo would be the name of the shared object file, okay, and then it's going to have these functions, which is get num rows, get number of columns, get row matrix, get UX matrix, run, and if you have to write an MRT, all those things later on. So essentially all these will be called with, from these functions that we have, okay, with the same names, so that you can call them from the Python interface, and then it can directly call these functions which are compiled in the C++, okay. So we need all this. So except for these, it is same as a regular C++ code, except for the Python binding we have done before and this ones. Now let me show you how to compile this. Okay, so I have this simple C++ command. So we have C++ minus some optimization, throw all the warnings, everything, standard C++ 1.1, and then it's going to use some Python to build the shared object file, okay, that is for this. FPIC is basically for that. Use all the includes that are required. We have done PyBind 11, include header, all those things. Then lbmdemo.cpp is the CPP file which we have just now looked at, and then -o, and it's going to basically generate an LBM shared object file which is called lbmdemo.so, okay. Now then we can use Python to load this lbmdemo.so and then call these functions, the run or get row matrix or UX, all those things, or even the LBM demo, the constructor, all those things. Fine. So I'm going to compile this and then see. Okay, it has compiled. 1037 is from just now, got compiled, fine. So that is that's good. So this is the shared object file, which is of so many bytes, whatever. Now let's look at the corresponding Python program so that we can run this lid-driven cavity code that we have written. So we say import LBM demo, which is that shared object file that we have just compiled, as LBD. Okay, we are just going to call as, whenever we say LBD, it's going to refer to this LBM demo shared object file. And then because we want to plot as it is computing, we want to import matplotlib pyplot as PLT. Okay, and then we will make some numpy calculation. So for that I have numpy as NP, and then some display things from the IPython. Okay, so then we want to, so let's see if this works fine. Okay, it has executed in some 2 seconds. Fine. Then what we have is NX and NY. These are basically your number of columns and number of rows. I'm setting the dimensions of the lid-driven cavity as 100 by 100. Okay. Then ULID is UBC. This is your UBC, which I'm setting it as 0.1. Then in here I'm calculating omega, which is your quantity that depends on the kinematic viscosity, from the Reynolds number. If somebody gives me Reynolds number, I can calculate omega. If somebody gives me omega, I want to calculate Reynolds number so that I know what Reynolds number I'm simulating. So I set Reynolds number equals 100, and nu equals, these are the number of points we have, times ULID divided by RE. That is the kinematic viscosity we have. Then omega equals 1 upon 3 times nu plus 1/2, right? This is the same definition that is there from the theory. Then it's going to also print omega. What is the value of omega? In case, let us say, if somebody gives me omega, then I can uncomment this part of the code and then comment this part of the code to calculate corresponding Reynolds number from the omega. Okay, that's all. Then I'm also calling this first function, which is basically LBM demo, that is the constructor, which is called from LBD, that is the shared object file, LBD dot LBM demo, and then we are passing on NX, NY, which is 100 by 100 by ULID 0.1 and this omega. Okay, so let me execute this. It basically printed omega equals 1.25 for this RE 100 and so on. Okay, that is the only thing I'm printing. If you want, we can also print what is nu kinematic viscosity and redo it. Okay, so it printed nu as 0.1 and omega as 1.25, and it has also initialized everything that is there in the constructor function, correct, that we have now called. Okay, then just to verify, we can also call this other function instead of get row matrix, get UX matrix, get UI matrix. So we can just print this and see. So it basically called that function, and then it initialized UX to 0 everywhere. So it basically shows bunch of zeros here. So that is the function call we are able to call from the Python interface. Okay. Now I'm setting, let us say, some 10 steps in a range of, for I in the range of 0 to 1000. That means in total I'm doing some 10,000 time steps. Okay, and what I'm doing is I'm calling this lbm.run, which is the SRT BGK that we have just seen. Okay, and it is going to call this for every 10 steps. Okay, yeah, 1000 times as such. Then I look at what is UX. UX, I'm going to get the value, which is lbm.getUX matrix, and then I'm also get UI equals lbm.getUI matrix. It's going to give me the UX and UI matrices. Then all I do is a contour plot, plot.contourf. So it's going to give a contour plot of, I'm only plotting UX. You can also plot UI or even magnitude of velocity, which is fine. And here this origin equals single quote lower. This is where we are hacking Python so that otherwise it will be the top left corner as 0, 0. So we are setting origin equals lower, which basically shifts it to be bottom left corner. Otherwise everything else will come out to be shifted. Okay, so your bottom will be the top, top will be the bottom, and so on. So it will get a little confusing, and you can choose your color map that you want. So I'm choosing cool, warm, and then we are doing clear output weight equals true. So it's going to clear the output and then do it again for every time step. It's going to do that, and then plot the color bar. We want to know what color represents what value, and then title. It's going to show F time steps. So it's going to show the flow time is so much number of time steps times delta t. That's what it's going to update, and then it's going to show. Fine. So that's what we have. So let's so questions so far before we run this. Fine. Okay. Let me try running this. So hopefully it will run. Okay, it's running. So you see the classical lid-driven cavity with Reynolds number 100. It's somewhat slower than what I anticipated, so you have to wait for 10,000 time steps. Okay, one thing you notice here is that I have applied the U lid to be 0.1 on the top. You remember we had the first line there. But again, you realize that that should be, I mean, although I'm referring to this as the boundary with a same distance as delta x, but it's supposed to be at delta x by 2 as such, correct? So I think that you understand in terms of how you interpret this data, correct, in terms of the boundary conditions. It was much faster earlier, I think it because I have Mathematica and a lot of other things loaded. Sorry? Maybe soon, yeah, okay. We will wait for it to finish. It's a double precision code actually. Yeah, correct. It was not so this slow actually earlier when I ran it. It was faster, but maybe now that you are all looking at me, it is slow, you know. Yeah, so this is kind of quite convenient if you want to see the results while the simulation is running, because you don't have to keep on loading the data into your other plotting software. So that's kind of very nice. Any other questions before we wait for it to finish? Have you used similar kind of setting before, like calling something from a interpreted language? No, not yet. Okay. It's kind of convenient because you don't have to recompile your code every time. You can just, let's say if you want to change something else, you can just change it here and run the Python code, so you don't have to compile the code again, right? Many times your code will have like tens of files, then the compilation itself will be slow, so which you don't want to change every time, yeah. The command line arguments you can use, but then you will have only a limited number of arguments you can pass, few of them. Correct. Yeah, input file certainly is useful, yes. But for visualizing the results as they are being computed, this is somewhat easy. Yeah, somebody was asking, this will certainly be slower than if I were to just call the C++ code, because now I'm making the control from the Python side, right? So I'm calling steps, I'm calling run every 10 steps. So that will basically slow it down, because every time there is a call from Python to C++. So if you were to run a pure C++ code, it will be somewhat faster. 100 steps. Yes. 10 is small. I think I should make it 100. That would have been better, yeah. No, I can even interpret if at all it is going to, because I think it usually converges by these many iterations. Let me see if at all it allows me. I'll say interrupt. Okay, it interrupted, but then we got some data, okay, that is there. Now, of course, I can't plot this anymore, okay. So what we have is, we have the reference data from GIA and GIA. So that data is what I'm trying to plot here, so that we can compare how our code is performing compared to the reference data, okay. So what we have here is that Ux is the x component of velocity, which we are extracting at ny by 2. That means we are looking at the halfway horizontal line, okay, along the entire x. We are calculating what is Ux, and then I'm normalizing with 0.1, because 0.1 is the lid velocity. So every velocity inside is coming out to be with respect to that. So that's what I'm storing it as ux vertical. Okay, this is basically ux on the vertical midline. Okay, that's what I'm extracting, and then y line mid, I'm again writing it as 0 to 1.0, right? That is the y line I'm defining. Then I'm loading what is the data from the GIA's paper into these two values, that is GIA y and GIA ux, where I have this GIA data u versus y.txt, which is somewhere here. Okay, so this is the reference data where for Reynolds number of 100 we have first column is the y location, second column is the u x values. Similarly, you have the data for different Reynolds numbers which you can run and compare. So this is one data which I am loading. Then I have this plot ux vertical, y line mid, and then the GIA data. Okay, so those two data I am plotting. One is with these markers 0, other one is in green color. Then we are labeling them. It's just very slow. Okay. Okay, let me plot this and see. Okay, so this is the this blue line is from the current simulation. These yellow symbols are from the GIA's data. Okay, that's what I have plotted. And this is for the ux, the x component of velocity along the y midline. Okay, half midline. Similarly, I have the uy velocity, that is the v velocity, plotted along the horizontal midline. Okay, that means along this we have the v velocity that goes down and comes up, and I have uy horizontal and then x line mid. These are the two variables I am loading into. Then I am also getting the GIA x and GIA uy. These are the x and uy from the reference data. Okay, as you can see, I have 0 and 1 here. If I change this 1 to 2, then I'm going to the next Reynolds number that is available. Okay, so this is 1 is the second column, which is the Reynolds number 100. Okay, then I plot all these things. Let's execute this. Okay, that's giving you again a very good match for the v component of velocity as a function of x line. Okay, so that's the entire code where we are able to do the lid-driven cavity, compare the data for Reynolds number 100 with the reference data. Of course, this entire exercise can be done again with for any other Reynolds number that you wish, and depending on the appropriate grid resolutions. Okay.
Will this BGK operator will work for high Reynolds number? Like, is there any limit of Reynolds number?
Okay. No, you can go ahead. Yeah. So the question was, does the BGK operator work for any Reynolds number, high Reynolds number, or is there a limit for it?
So in principle, the BGK operator works for any Reynolds number as long as you provide enough resolution.
Yes.
So for high Reynolds number, it may be becoming difficult to provide enough resolution, and then there are other collision operators that can do the same thing, that would actually be appropriate and able to do simulations at that particular Reynolds number at a relatively low resolution, where the BGK is not able to reproduce the data at this particular Reynolds number. But in principle, the BGK operator can be run at any Reynolds number, provided you provide enough resolution.
If I want to fix the Reynolds number, I can use any value of like viscosity, right? Tau. So what tau I can choose for will the results depends on this tau?
Okay, I think the result depends on tau. The result will depend on tau. So, I mean, the error will depend on tau. The other thing is, if you change tau and keep the resolution the same, then you have to change the Mach number, and then the Mach number error will change. So there are disadvantages of having very high Mach number, and there are disadvantages of having low Mach number. Both of them may lead to the one is asymptotically bad and the other one is numerically bad, saying that in one case you increase the Mach number error, in the other case you increase the round-off errors. So there's always a range, where it makes sense to operate. Yes, and regarding your other question, I don't really know, but I think one of my students figured out that you can run the BGK there with an omega of up to 1.95, and if you go higher than that, it will crash. Yeah. So by experience, yeah.
I think you are now familiar with all the steps that we have in LBM, correct? Okay, fine. Then if there are no more questions, we will stop here. Okay, and then we will meet in the afternoon, and we would like you to work on the LBM code yourself. Okay, so we'll be there to help you answer your questions, but then you can do a hands-on of this thing so that you get used to it, and next week will be much more, you'll be convenient with these codes. Okay. Fine. All right. Yeah. Thank you very much.